Hey, what's up, everyone? Welcome back to my YouTube channel. And for those who are new here, my name is Gloria Kambua. Some of you have been asking me to make tutorials about data structures, and I'll be making these videos alongside our Code Newbie programming series. Okay, so data structures is a little bit advanced, and if you're new to programming, I advise you to stick with the basics first before you cover data structures. Okay, let's get started. What is a data structure? A data structure is a way of organizing data so that it can be used effectively. And that's all what a data structure really is. It's a way of organizing data in some fashion so that later on it can be accessed, queried, and perhaps even updated quickly and easily. So why data structures? Why do we use data structures? First, they help manage and organize data. They will help you make your code cleaner and easier to update, and data structures are the essential ingredients in creating a powerful and fast algorithm. Before we even talk about data structures, we are going to talk about abstract data types. What I'm talking about is the concept of an abstract data type. What is an abstract data type and how does it differ from a data structure? Well, the answer is that an abstract data type is an abstraction of a data structure which provides only the interface to which a data structure must adhere to. The interface does not give a specific detail on how something should be implemented or in what programming language. One particular example is that suppose you have an abstract data type for mode of transportation to get from point A to point B. We both know there are many modes of transportation. So which one would you choose? One might consider walking, biking, getting on a bus, and so on. These specific modes of transportation would be compared to the data structures themselves. Here are some examples of abstract data types on the left hand side and some possible underlying implementation on the right hand side. As you can see, a list can be implemented in two ways. We have dynamic arrays and linked lists. They both provide ways of adding, removing, and indexing elements in a list. Next, we have a queue and the map abstract data types, which themselves can be implemented in various ways. Notice that under the implementation of a queue, I put stack-based queue because yes, you can have a queue which is implemented only using stacks. These may not be the most efficient ways of implementing a queue, but it does work and it is possible. What I'm trying to say is that the abstract data type only defines how a data structure should behave and what methods it should have, but not the details surrounding on how those methods are implemented. Alright, now that we are done with abstract data types, we need to have a quick look at the world of computational complexities. To understand the performance of our data structures. So as programmers, you'll often find ourselves asking these two questions over and over again. That is, how much time does this algorithm need to finish and how much space does this algorithm need for computation? So if your program takes a lifetime to be executed, then it's no good. Similarly, if your program runs in a constant time but requires a space equal to the sum of a really large space, gigabytes, then your algorithm is also useless. Then that's when the big O notation comes into place. To standardize a way of talking about how much space and time is required for an algorithm to run, theoretical computer scientists invented the big O notation, among other things like the big theta, big omega, and so on. But we are only interested with the big O as it tells us about the worst case and it also indicates the upper bound of the function. Big O notation only cares about the worst case. So if your algorithm sorts numbers, imagine the input is the worst possible arrangement of numbers for your particular sorting algorithm. Or for example, suppose you have an unordered list of unique numbers and you're searching for the number 8 or the position where number 8 occurs in your list. Then the worst case isn't when 8 is at the beginning or in the middle, The worst case is when 8 is at the very last element in your list. For that particular example, the time complexity would be linear with respect to the number of elements in the size view list, because you have to go through every single element until you find 8. The same concept applies to space. You can just consider the worst possible amount of space bytes that your algorithm is going to need for that particular input. Also, there is this concept that Big O only cares when your input is large. We're not interested in what happens when the input is small. And for this reason, you'll see that we're going to be ignoring things like constants and other factors. In our Big O notation, you'll often find these coming up. And to clarify, when I say n here, n is usually going to be the input size coming into your algorithm. There is always going to be some limitation of size n. And we have the constant time, which we refer to as a 1 wrapped around a Big O. We have a logarithmic amount of time, which we say that it's a Big O of log n. And if your algorithm is linear, then we just say it's a Big O of n. And if it takes like quadratic time or cubic time, then we say that that's n raised to the power of its exponential. Usually this is going to be something like 2, 3, and so forth. Basically, any number that is greater than 1 to n. Now, we're going to be talking about properties of Big O. And to repeat what we just said earlier, Big O only cares about what happens when the input becomes really large. We're not interested in what happens when n goes to infinity. This is how and why we get the first properties. First, we remove constant values added to our Big O notation. So, like as you can see in this example here, we have O and we have n plus c in brackets. Using simple mathematics that we learned in, I think, class 4, when you open these brackets, we'll get that it's O of n plus O of c, where c is the constant. And we are going to ignore the constant because any number added to infinity is equals to infinity. Therefore, our solution will be Big O of n. The same applies to multiplication. If you open the brackets for multiplication, Big O of Cn, we are going to get Big O of n, because any number multiplied to infinity is also an infinity. Now let's look at this example. F of n is equals to 8 log n cubed plus 12n squared plus 2n plus 3 plus n to the power of 4. N to the power of 4 is the biggest in this function, and therefore Big O of f of n will be equal to Big O of n to the power of 4. Alright. Now let's look at some concrete examples of how Big O is used. Both of the following run in constant time with respect to input size, and because they don't depend on n at all. On the left hand side, we have assigned A to 1, B is assigned to 2, and C is assigned to A plus 6B. And on the right hand side, we have a while loop, and we are saying while I is less than 11, keep on running the loop until we get to 10. Both of these don't depend on n as they are running in a constant time. As our input size becomes bigger, well, the loop is going to run in the same amount of time regardless. Now, let's take a look at this next example here. We have two algorithms that run in a quadratic time. The first one might be obvious, since any work done n multiplied by n will be equal to n squared, and therefore our Big O of f of n will be equal to Big O of n squared. But let us observe the loop on the right hand side. Here we have changed the second loop, which by the second loop I mean 4 of j is equals to I, j less than n, j plus plus. And as you can see, I goes from j is assigned I instead of a 0 as compared to the first to the loop on the left hand side. So since I goes from 0, to n, the amount of looping done is going to be directly related to what j is. And remember, I is changing from the outer loop. If you fix I to be 0, we are going to do n work. If you fix I to be 1, you're going to be doing n minus 1 work. If you fix I to be 2, you're going to be doing n minus 2 work, and so forth. The question then becomes, what is n minus 1 plus n minus 2 plus all the way to 1? Well, this is a well-known identity, and this turns out to be n plus n minus 1 plus all the way to plus 1 is equal to big O of n squared after it has been solved. Now, let's look at perhaps a more complicated example. Earlier, you may have been wondering, well, how do we get this log arithmetic or linear arithmetics or time complexity? Here is a classic algorithm of doing a binary search which yields a lot of algorithmic time complexities. So what this algorithm does is it starts by making 2 pointers, one at the very start and one at the very end of the array. Then it selects a midpoint between the two and checks if the value we are looking for is at the midpoint. If it is, then if it has found it, or if it has not found it, if it has found it, it stops. It returns the value and it discards the other half of the array. If it has not, it has just either the low or the higher pointers, and even the worst case scenarios, we discard the half of the array each iteration until we get our value. So if you do the math, the worst case is we will do log base 2 of n iterations, meaning that the binary search runs in logarithmic time. Here is another example worth going over. So first notice that there is an outer loop with a counter I that does n work, and then notice that there are 2 inner loops, one that does 3n work and the other does 2n work. So the rule we use to determine the complexity of this algorithm is to multiply the loops on different levels and add those that are on the same level. So using this rule, you're going to see that it can take n work to do the outer loop. We multiply by 3n work to do the second loop, and then 2n work to finish the third loop, which gives us a 5n squared, after calculations, which is big O of f of n will be equal to big O of n squared. Alright, the next one is very similar to the previous example that we just looked at, and on the outer loop we have I is going from 0 to 3n work done, and on the outer loop, and the second loop goes from j goes from 10 to 50, so that it does 40 loops. That is a constant 40 amount of work done, and plus however the third loop, which is j less than n cubed plus j is equals to j plus 2. We can see that j is a little bit escalated, so that loop is going to be finished a little bit faster than the others. So we are going to get in the inside, which is 40 plus n cubed divided by 2, because j goes j plus 2, and we are going to multiply it with the outer loop work, which is 3n. After opening the brackets and solving it, we will get 3n over 40 plus 3n to the power of 4 divided by 2. And as you can see, 3n to the power of 4 is the biggest in this function. Therefore, our big O f of n will be equal to big O of n to the power of 4. And that's it for today. Thank you for watching. Don't forget to like, share, and subscribe. Cheers.